record. So let's record. We are now recording. This is our first slide. Happy Tuesday. Okay, so if there are no questions, we will continue with this process of funness. Okay, so the problems, what I asked you to do for the homework, I asked you to do a couple things, like show it's increasing, show it's bounded. So here's how you do that, or at least one way to do that. So what we do is we say this sequence is increasing. Why? Because the nth term is always greater than the guy who came before it. So let's be very clear with this. The nth term is greater than the previous term. So what does that mean? Another way of saying that is that the a sub n is always greater than the guy who came before it, a sub n minus 1. So there's no other way of writing what it means to be increasing than to write this. And this is true for each n, whether n is 1, 2, 3, all the way out to infinity. It's always true. So how do we verify this? Well, this we can just use algebra. So how can we verify it? Well, let's take the nth term and let's compare it to either the guy who comes before or after. So if I look at the list, it's clear. I mean, it should be to you, if you look at this list and you look at, for example, the first and the second, or the second and the third, it shouldn't take you long to figure out which one's bigger. As you move to the right, the numbers are getting larger. If you read this list from left to right, the numbers are getting larger. If you don't believe me, you need to convince yourself of that, either algebraically or plugging numbers into a calculator and getting decimals. But for this particular sequence, the values are increasing. Now, how do you verify that mathematically? We can use algebra. So let's take, how do we show something's greater than something else? So let's take the nth term and let's do some algebra. So let's look at the a sub n. This guy is greater than the previous guy if the following is true. Well, let's plug in what each one of these means. So this guy is 4 times n over 6 times n plus 1. And the guy on the right-hand side is 4 times n minus 1 over 6 times n minus 1 plus 1. So if I do what we call in algebra clearing denominators, or you might have called it something like cross multiplying. If I perform this algebra, well, maybe I'll even clean it up first. Let's clean it up, the right-hand side first. So this is 4n, and then this is 6n plus 1. And so over here you had 4n, it would be 4n minus 4, and then it would be 6n minus 6 plus 1, which would be 6n minus 5. And so if you do some cross multiplying, this is the same as 4n times 6n minus 5 greater than 4n minus 4 times 6n plus 1. So what I'm doing is I'm doing logical reasoning. I'm trying to trace this inequality to something that's obvious. This is an argument that is sort of used in advanced mathematics often, so it's a good time for us to learn all about it. So if we multiply everything out, we have 24n squared minus 20n, and then on the right-hand side, 24n squared plus 4n minus 24n minus 4. And if we sort of get rid of some things that are immaterial, like we have two things on the same side that we can sort of ignore, so I'll get out my red marker and say, hey, this guy and this guy can go away. If we put everything on one side, we get 4n, because 24 and 20, if I take the difference, is 4. And then I have 4 more, so this becomes 8n. Yes or no? Actually, they all add up to what? So let's keep that in mind before we go do anything. What's 20n? Over here, I have 20. And then these guys cancel. And so what are we left with if we didn't make any errors? We are left with the following statement. We are left with the statement of 0 on the left-hand side is greater than negative 4. Which is true. So what we just did is we just proved a sub n is greater than a sub n minus 1. That's what we just did. Now, this is something that's an unfamiliar argument to many students in calculus, but it's an argument that you should try to understand. It's clear to all of us that 0 is bigger than negative 4, so if you retrace this argument from bottom to top, you get that the sequence is increasing. Does anybody have a question? Comment?
You stay on the slide for just a second.
I can. I'm not going anywhere, Mr. Darrell.
Thanks, sir.
I have a question.
Yes.
So whenever we want to prove if it's true or not, we just set up the inequality and solve it?
That's one way to do it. This isn't the only way. This is one way. Yes.
Okay.
And you know, another way, an alternative way would be to use calculus. You could take that expression and take the derivative. And if the derivative is positive, you can, so let me write that down because sometimes that's an easier way. So here's an alternative method. An alternative method is to let f of x, which is the corresponding function, that would be 4x over 6x plus 1, and show that f prime of x is greater than 0. So you might remember from Calc 1 that if the derivative's positive, the function's increasing. So this is an alternative method. Does that make sense? And then, of course, the alternative, if you have, I need a sweatshirt, I'm cold. If you have, if you wanted to show decreasing, you could show the derivative's negative. Okay, does anybody else have a question about this? Okay, so that's what it means for a sequence to be increasing. This is an example of one. Now, the next thing we want to do is we want to show that it's bounded. So that's what's next. So how do I know it's bounded? Well, every term is clearly what? Well, every term is clearly, let's look at this. The sequence is 4n over 6n plus 1. So there's no negative numbers here. So it's clearly always positive. So that's what we call a lower bound. Now, what can you say about 4n over 6n plus 1? Well, you can always say this. Here's something that many of you might kind of not, you maybe have not thought of numbers this way. But the fraction on the left is clearly going to be a smaller number because its denominator is larger. So we can actually write this as 4/6, which of course is 2/3. So there's names we give to these numbers that are very important, particularly in advanced math. We would call this a lower bound. And we could call this number an upper bound. So the big jump is this intermediate step right here. So you really need to convince yourself of why this inequality is true. And if you don't see it, then multiply it out like we just did before to verify that it's true. Again, this is an argument many of you have probably never seen before. One of the big reasons calculus is difficult is because it's the first math class most of you have taken where it's not all procedures. We're asking you to think. We're asking you to learn things that don't necessarily become easy to learn after 2 seconds. There's very few things in this class you're going to learn just by watching me do it. Most of it is a struggle to learn on your own. And this is a good example of that. Does anybody have a question about that? So this inequality trick that I did right here, this idea, so I want to single this out because it's going to show up again later in the go. This is a standard trick. What we call this in the math world is we call this number sense. I don't care what number n is. The left-hand fraction is always going to be smaller than the right-hand fraction, always.
Can you go over how you got 2/3?
Well, what's 4/6? Reduce it.
2/3, okay.
Make sense?
Yeah.
Ah. See, this is the difference between your generation and mine. You guys are just like 4/6, throw it into a calculator. I'm like 4/6 is 2/3.
And how you got the lower bound?
Well, because they're all positive. Can this number ever be negative? The one I'm throwing my pen around, can you see that? This guy is never ever negative. So I can easily say that it's bigger than 0. That's not the only lower bound, it's just 1.
Wait, couldn't it be negative if the n value is like less than a 6th?
Right, but less than a 6. Well, n can't be any smaller than 1.
Well, if we define it that way.
Well, that's exactly how we've defined our sequences.
Okay.
Remember, our definition of a sequence is that it is a function. So the smallest value the index can ever be is 0 or 1. So if you want to get real particular, which is fine, you can get real particular. If you want to get really particular, you can handle that by just saying this. If I put a less than or equal to, then if n is 0, then it is 0. But it's never going to be smaller than 0. Okay, so then the last part of this problem is to determine the limit. Well, to determine the limit, we don't even need the above stuff, but we're trying to teach you how to analyze, so that's why we did that. So what's the limit? So the limit as n goes to infinity of 4n over 6n plus 1 is, from Calc 1 knowledge, you could think of this a few ways, but let's do it the longhand way. The longhand way is, if I do some manipulation, if I factor out an n, I have 4 over 6 plus 1 over n, and that equals 4 over 6 plus 0, which is 4/6, which of course is 2/3. So we can use those tricks we used in Calc 1. Another way to do this, the shortcut, is to just look at the leading coefficient, the 4 and the 6. And don't forget, most of you learned how to compute these types of limits even before calculus. They didn't call them limits then. They called them, you were in an algebra class, you would have been studying horizontal asymptotes. So here's something I'll leave you with that would be useful. So to get a better idea or a better visual, use Desmos or anything, I don't care. You think I get paid by them. But use Desmos to graph this function, f of x equals 4x over 6x plus 1. What you're going to get is you're going to get the following picture. I'm going to just do it in the O'Grady way here. So if this is my x, this is my x and y axis. So what does this function look like? Well, we know it has an asymptote, a vertical asymptote, it has a positive asymptote. But if I want to look at what this graph looks like, it's going to look something like this. It's going to come up the following way. When I plug in 0, I get 0. So this guy it's going to look like this. So what it's also going to have, if it's going to have two asymptotes, it's going to have a vertical asymptote here. And then it's going to have a horizontal asymptote. Here. So where is the horizontal asymptote? It's going to have a horizontal asymptote at y equals 2/3. So anyhow, this is some stuff we studied back in Calc 1, but this sequence is, and let me make that a little more clear. Clean, darn it, I didn't want to get rid of the whole stupid thing. But I should make it a little cleaner. We studied these types of functions in Calculus 1. And the sequence is very much associated with it. Does anybody have a question about this? Now you could do a very similar analysis for problem 4. Does anybody have a question? Comments? All right. Got chaos upstairs, guys. Woo. Okay, so that's a sequence. So problem 5 is to help you illustrate the difference between a sequence in a series. So let's show you how to analyze these creatures. So to answer 5 and beyond, you need knowledge about series. And as I said last week, this stuff is not easy to learn. It's just not. So here's what we know so far. So here's what we know so far. First off, we know the definition. We know how to define this. If we have a list of numbers, we know that this is equal to a limit. It's equal to this limit. So how do we say this? What is this called? What is the language for this? This is called the limit of partial sums. Ooh, we got lecturing happening upstairs. Parenting 101. This is fun. All right, the other thing we showed, and this is it, all we showed so far is that we showed this particular series, which was 1/2 k equals 1 to infinity. We showed this thing. Remember what this is. This is 1/2 plus 1/4 plus 1/8 plus 1/16, and we learned that this goes on forever and ever and ever. And what we showed is that this thing was actually equal to 1. That's what we showed last class. This is the only thing we know about series right now. But we're about to learn that this thing, number 2, is actually a very specific case of a general problem. So, does anybody have a question about this? Okay, so if you don't have questions, let's see what this gives us. It actually gives us tons and tons of information. So, the proof we gave of 2 above can be modified. To prove a theorem. So here we go. Here's the following theorem. Let R be any number between -1 and 1. Now, why am I using R? I don't know. I can use any letter on the planet. I'm using R. It's convention. Most books use R. Then this series, the series k equals 1 to infinity of R to the power k. So in the previous problem, what was our R? It was 1/2. If you look at homework question 5, what is your R? It's 4/5. If R is between -1 and 1, this series, which would be R plus R squared plus R cubed plus R to the 4th, so on and so forth, has a very nice sum. It is R divided by 1 minus R. So you can check this with the problem above. If R is 1/2, what do you get? You get 1/2 divided by 1/2, which is 1. So let's put a nice big colorful creature around this because it's so beautiful.
I thought that was just the weird exclamation point thing. No, that's a sum.
No, you're
Yeah,
thinking of
summation.
Cheryl, yeah, no. You're thinking of the weird exclamation thing. That's
Where it's like 5
factorials. Yeah, no, you're thinking about combinations from. You're probably thinking of like n choose k or something with exclamation points in it. Those are called factorials. That's slightly different. In fact,
Okay.
completely different.
Yeah.
So this is a very important result. So let's apply it to what we just did. And then if you have questions, as I said, please, please, please ask. This is not easy to learn. So let's switch up colors. Let's go to this light blue. I guess I need, uh-oh, my house is about to collapse. So if I take 1/2 to the power k, like we just did in the previous, we did on Friday, this is equal to, by the theorem, 1/2 over 1 minus 1/2, which is 1/2 over 1/2, which is 1. So if you want to understand how I'm using the formula, let's look at the numbers I'm using here. Here, what is R? R is 1/2. So that's the one we already did. Let's do one that we didn't do. So this can be similar to the homework. How about we go k goes from 1 to infinity of, how about 4/9? 4/9 is between -1 and 1. So this sum is 4/9 over 1 minus 4/9, which is 4/9 over 5/9, which simplifies to 5/4. So once again, what are we dealing with here? What is our R here? Here our R. Four nines. Does anybody have a question about this? Now, I'm writing this all in compact form. Don't forget what this means. I mean, this is a compact form for a sum.
What would happen if R was negative?
Ah, so that's the next step. Bad things. So if R is negative, the series diverges, nothing. Or if R is bigger than 1. It's so funny. Whenever you talk about this, my phone just popped up because Siri thinks I'm talking to her because I said the series diverges. So now my phone, Siri wants me to answer questions. It's very strange. Yeah, so, what's that?
Ask Siri to divide 0 by 0.
Yeah, what will she do?
Oh, just listen.
Siri, divide 0 by 0.
Oh my God.
Siri. Now she's not going to listen. Siri. Siri. She's not listening. This jerk. Siri. Oh well, we're not. She don't want. Now she doesn't want to talk to me. Evil. All right. So.
She got offended that you didn't want her before.
Oh, I know. So this is a very important thing to get from here. So note, if R is less than -1 or equal to -1, or R is greater than or equal to 1, the series diverges. It doesn't have a sum. And here's something, and I don't mean to say this to be like negative, but if you haven't thought about calculus since last class on Thursday or Friday, and you're already like, what does diverge mean? I mean, you're making it that much more difficult to learn this. This stuff is going to be really hard to learn unless you give it some attention, every day, whether it's 20 minutes or a couple hours. You got to give it some attention. So these series have a special name. They're called geometric series. So it's worth us pointing that out on the next page because it's nice to give names to things that have special behavior. So these series, whether they converge or diverge, oh, kid can't spell. So since it's a proper name, we'll say they're called geometric. And if you ponder that for a second, if you think about why they're that, it wouldn't be that difficult to understand. They're very natural in nature. For example, many of you have seen like a ball. If you drop a ball from a certain height under gravity, you can analyze how it will bounce up, how far will it bounce up the second time, the third time, the fourth time. And then you can do things like get the total distance it travels. So these kinds of creatures are very much useful for many reasons. Does anybody have a question? So here's the thing. Geometric series, if you look at the homework, that's what we're studying. We're studying different geometric series. So here's a very important fact, though, that you need to pay attention to. And I'm going to point it out now. So the formula, what we wrote down before, this formula, r to the power k. I know this is scary because there's all these letters here, but this formula that's r over 1 minus r, this guy depends on where k starts. If k doesn't start at 1, the formula changes. So if you look at a lot of the homework problems, it doesn't always start at 1. Sometimes it starts at 0 or 2 or 3. So the formula changes. Now, I'm not going to go through these arguments, but you can do them. It's just a little bit of algebra. I'll give you one of them, and then the rest you can deduce on your own, hopefully. Oh my God, do you hear that upstairs? I think my kids are fighting each other. Okay, so this is important. So for example, if I start at 0 instead, the formula is now 1 over 1 minus r. You should do the algebra. So, I mean, it doesn't, you're not going to learn it if I show you it. You just got to write it out and then just do some algebra. It's only one line. It's not a ton of work. All right, does anybody have a question about this? So let me give you a couple hints for the rest of homework. What is this, homework 8? Is this homework 8? Yeah, homework 8. I think, what did we start with? Did we say this was homework 8? I think. Yeah, homework 8, yeah. Okay, so let's do that, and then we'll move on. So, where did we leave off? We left off, I believe, with problem 5. So we've now taught you how to do problem 4, 5, all the way up through 5, and you now know how to do 6. But 6, you have to be very careful because they don't all start at 1. So here's some hints for 6. So for 6A, R equals 9/4. 9/4 is clearly greater than 1. What about for B? Well, the hint for B is there's another way to write -2 or 2 to the -3k. When you were in elementary algebra class, you learned exponent laws, and this is the same thing as 1/8 to the power k. I don't think you'll need, for C, and this is going to be important, you need to note where k starts. For D, you need to note that E is less than pi. And then I'll skip E because E, there's, you can think about that on your own. But then for F, you need to realize that 3, say, to the n plus 1 is just 3 to the n times 3. So you need to think about how you can simplify that fraction to make it look like a geometric series. You'll notice that F is not obviously a geometric series. You need to make sure that it is. You have to do some algebra.
If you do it r to the 0, if k is 0 and it's r to the 0, would that just mean it's the series plus 1?
Well, that's exactly right. Yeah, that's what I'm saying. If you look at what I'm saying, look where I have at the top of the screen where I say suppose k starts at 0. So the first term would be 1, right?
Yeah.
So if you take the formula and then add 1 to it and do the algebra, you get this. That's why I'm saying it's not hard to see why this formula moves. The formula is not hard to figure out if k is 1, 2, or 3 where it starts. You just have to figure out the algebra. It's just.
I mean, I just did the algebra. My desk is a whiteboard as well, so like I just did the algebra real quick.
That's exactly what it is, and it's very useful. I'm not even saying you need to memorize all these formulas. If you know one of them, you can deduce all the other ones just by doing simple. And it's really not algebra. Really, it's just you're subtracting or adding a number. That's all you're doing. To get the formula that's on the whiteboard right now, you take the old formula and add 1 to both sides, right?
Yeah.
If you want to get the formula for part B, you take the formula. Well, you already have that formula, but say C. Say you want the formula for C, number 6C. All you do is take the formula we gave you the beginning of class and subtract 1 from both sides. That's all you do. So it's just arithmetic. Don't overthink it. So let me give you a hint for 7. So for 7, you need to note that 1 plus 2/3 plus 4/9 plus 8/27. This is just, we can write this in a compact way using this sum. It's the sum. K goes from 0 to infinity of what? It's just 2/3 to the power k. You have to make that connection. If you make that connection, the problem's instant. And that's it for this homework. Does anybody have a question, comment, concerns? Anything? Oh my God, do you hear that? My house is... What's happening up there? Is everybody alive? It's crazy. It's like living in an apartment with people that are assholes above you. Okay, does anybody have any questions about this? Does anybody have a question? Okay, so we need to sort of think about where that leaves us. So what's next then?
So wait, if k is 0 and you're just adding 1.
What's that?
K is 0 and you're just adding 1, and then you go to, like, say k is 3. So you would just start at like 1 over 2 over 3, or sorry, 1 over 1 minus 2 over 3 to the third.
Whoa, 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 whoa,
One to
whoa,
the
whoa.
third.
No, that's not how it's gonna, no. Look, so let's do that. Okay, let's hold on this for a second. Let's see, for example, how we can get formulas for this. So let's say we'll do one of them. So let's see how to handle, whoa. I hate when it does this. So let's see how we might handle 6c. So what do you have? So you know, for example, that if you start at 1,
Mm-hmm.
we know that if you start at 1, you have this formula. You have r over 1 minus r. So this implies that if you add 1 to both sides, like you suggested, so if I add 1, 1 is just r to the 0. Then that would be the same as this. So let's just, let me be more clear. Let me do more than just 6c. So if I go up here, if I get my eraser, so let's see how to handle 6 when k, let's write it, let's phrase it this way. So let's say when k starts at 0 or 2. So if I take my fact right here that we started with, we did this last class, I add 1 to both sides. Well, what does that tell me? That tells me that then, this tells me that my sum starting at 0
Can you go back to the last slide, please?
Yeah. What's up? You got a question about it, or are you just copying?
Yeah, I just need to get the notes for it.
All right, cool. Let me know when you're ready.
Okay, you can go ahead.
Okay, so if I look at the left-hand side, I can rewrite the left-hand side is this, and then I won't even touch the right-hand side yet. It's still this. So now I'm just going to do some algebra. I guess I don't even have to do this. We'll just do the reasoning on the right-hand side. So now I have a number, so let's write 1 as 1 over, or 1 minus r divided by 1 minus r. And so if I add these together, I get this. As we stated a few boards up. So now that's where the formula, if you start at 0, it's 1 over 1 minus r. Now, what if k starts somewhere else? Well, what if k starts at, say, 2? Well, you just have to reason the opposite way. Instead of adding 1, so for this guy, so notice that you have, if you start with k equals 1, again, this is r over 1 minus r. Now, we don't want the first term. What's the first term? If I don't want the one term, I have to think of this as, now instead of it being 1, this is r plus this. So I'm taking off the first guy. So notice that this argument's slightly different. So if you look at the second equation on this board, all I'm doing is from the second to third equation, I'm taking where my k is and I'm switching my index. So I'm pulling the first r out. R to the power 1 is just r, so I pull it off. So if I pull it off, instead of me writing the sum k goes from 1 to infinity, it's r plus the sum k goes from 2 to infinity. And then now you just subtract r from both sides. So if I subtract r from both sides, now I'm left with r over 1 minus r, or if you'd like, so do the algebra now, get it over a common denominator. So you guys can do this algebra. If I have r times 1 minus r, what are the numerators going to become? Well, so again, it's what I would encourage that you do is that you work it out. You have r minus the quantity 1 minus r times r over 1 minus r. And if you do the math, so again, if I take this down here and I just combine these two guys, or you don't even have to combine them. You can just do it this way. It doesn't matter. But what I'm saying is you could rewrite this if you so desired. And then what do you have? You have r, the numerator would be r minus r times 1 minus r, which is r minus r plus r squared. So you just get r squared over 1 minus r. So again, do you have to do this? No, you can reason in other ways, but this is one way of doing it. Does anybody have a question about this? comment.
Makes more sense now.
What's that?
That makes more sense now.
I'm
Thank
not
you.
even saying this is the best way to do it. I'm saying it's one way to do it.
Mhm.
Another way is to just reason case by case. There's, I've always said to you guys, I'm not big on memorizing formulas. What I think is more important is that you understand how to deduce formulas, not that you can memorize them. All right. So anyhow, that should give you enough tools in your toolbox to finish this homework. The question then is, what's next? I mean, here's the good news. Here's the bad news of all this. And I don't know that you're going to want to hear it, but here's what it is. So good news. Geometric series show up a lot and are, in a relative sense, easy. Now, you're going to say, this ain't easy. Well, guess what? If you practice it, it does become easy. And then when you compare geometric series to series in whole, or as a whole, they're very easy. Here's the bad news. In general, series are not so quote unquote easy to analyze. So what we're going to do then is we're going to do what we do best in science. If we can't understand something in general, we break it down into cases that we can understand.
You have like baby velociraptors upstairs.
I don't know what's happening. It's insane. That's what they're doing. It's like it's absolutely out of control, but you guys have no choice but to deal with it. What's the alternative? I don't know what the hell they're fighting about either. So what is the strategy then? The strategy becomes does a series converge or diverge? That's what the strategy becomes. We're not going to say what is the limit. That's too hard of a question to answer. So we're going to say, okay, series are complicated. We're not going to ask what the limit is. We're going to ask a more general question that's perhaps easier to answer. We're going to ask, does the limit exist? That is, does it converge or does it diverge? That's the main goal of what we're going to spend the next couple classes on. I don't know if that makes sense right now from this perspective. Someone wants to know if we have velociraptors upstairs, because that's all you hear. The kids. I can't figure that out yet. What's wrong? We got chaos. All right. Anyhow, that's where we're going to go the next few classes. Does anybody have any questions about this? So what you need to do is you need to finish this homework, because we're going to go on to completely new stuff on Thursday. And I don't mean to be the messenger of bad news, but the new stuff on Thursday is going to be a little more conceptually more challenging than this stuff. So, all right. Any questions, comments, concerns? As I always say, feel free to email me about homework. I would do my best to answer it as quickly as I can. Does anybody have a question? Going once, going twice.
For the fundamental theorem of calculus,
Yes.
like for the ln of 5 one, would the limits for the integral be 0 to 5?
No, it'll be 1 to 5. 1 to 5.
It'll still be 1?
Yeah.
What's the 5 for?
Because I'm asking you what the log of 5 is. So I think what the question is that you're asking, here, I'll do it on the next homework, or the board, in case anyone's interested. If you're not interested, feel free to to leave. I'm not going to be mad. So here, let me show you what I mean. So get a color that's worthwhile. So what was this, homework 5 or homework 6?
I think it was 6.
I don't know.
One of them.
Let me pull it up just to be sure, so if anybody's paying attention, they don't get confused. No, this would be homework 5. Yeah, so the problem you're talking about, I believe, is problem 6 on here.
Yeah.
So here's what you need to note. So the FTC says the following. FTC says that f of b minus f of a equals the integral from a to b of f prime of x dx. That's what the FTC says, right? So if we pick the appropriate f, that is, if we pick f of x to be the log of, say, x, and we pick b to be 5 and a to be 1, now you're going to say, why not 0? Well, the log of 0 doesn't exist. Also, what's important to note is if you do this, you get log of 5 minus log of 1, which equals this integral, 1 to 5. What's the derivative of log? It's 1 over x. But the beautiful thing about choosing 1 is that this guy goes away. This is equal to 0. So what you end up getting is, since the log of 1 is 0, so you get that the log of 5 is this integral. And so what I'm trying to do is I'm trying to get you to understand that if you go to the computer or you just hand do it, if you do a numerical integration on this integral, you're going to get the same number that you get when you calculator if you plug log of 5 into a calculator. Does that make sense?
Okay. Yeah.
I mean, this is a more conceptually challenging problem. It's not obvious. It's, again, it's what I said earlier. What you need to sort of come to terms with, and this is not to make you guys feel stupid or to make you feel like you're not smart, because this is the hardest part about everything, is you no longer are in memorize a procedure and do it over and over again. That's not math. All that crappy math that you guys learn when you're in school of solving and solving and solving, that ain't math. That is procedures that we call math class. What makes this stuff difficult is that each problem is so unique to in and of itself, and it's a challenge. It's a problem solving. It's deductive reasoning. It's not just memorizing some procedure and repeating it. So that's what makes this hard. Now, of course, you're going to say, well, I liked it when it was easy procedures to memorize. But the problem is that's procedures are things we can teach computers to do. Right? We need you guys to be able to do things that only the human brain can do. So this is what we want you to do. Does that make sense? I don't know.
I have another question.
Yeah, sure. What's up?
I think it was for homework 6, 2B, the differential equation.
Yes.
We ended up, I think we had to do the quadratic formula, but
Formula?
we have, I think, because when you like reduce it to get y's on one side. And
I don't know what the heck you're seeing. Let me see. This is homework what? Homework number 5, or no, homework number 6, 2B?
2B.
Yeah, so if you think about this, what you should have is you should have 2y minus 4 by equals 3x squared plus 4x minus 4 dx. And so if you integrate that, you should get, I see what you're saying, you get y squared minus 4y, right? And then on the right-hand side, you get x cubed plus 2x squared minus 4x plus c. So yeah, you don't really, I see what you're saying. You have, it's a mess. So here's a way to think about this, is solving for y is not fun. That's a good way of saying it. But you're correct. If you wanted to do it, you would have to use the quadratic formula. And the crazy thing about it, is this you, Kathy? I can't tell. I think it's you.
Yeah, it's Kathy.
Yeah. So the crazy thing about it is you need the quadratic formula, and you need to think about it as, you have to use the quadratic formula. And I'm not even saying you need to do this. You could leave your answer just as this. This is fine.
Okay.
Yeah. So if you wanted to solve for y, which some people would maybe want to do, some people wouldn't. So you would use the quad formula with what would be your coefficients? Well, your a would be 1. Your b would be -4, right? And then what would your c be? Your quote-unquote c. Your c equals star. And what is star? This whole creature up here would be star. This whole massive thing. So this thing, let me use a different color. And I'm not saying you have to do this. I'm just saying if you wanted to. If you wanted to get an explicit solution.
Okay.
So this is star. So the way I would tell you to think about this is yikes. It's not fun. But you can leave it just as it is up there, y squared minus 4y. That's completely fine. Because what we have now is we have an equation that relates y and x. And one of the things I didn't talk about in class, but it turns out to be the case in real life, is that oftentimes when you solve a differential equation, you get left with something like this, where you can't solve for y explicitly. Does that make sense?
Yes. And then, do you remember, I think, I'm not even sure which one this is. Homework number 6, 1F. You said it was really hard, and I looked it up, and they were talking about, like, polar and non-polar.
No. You're thinking at it the wrong way. You don't want to tell me what the value is. I'm not asking you to do that. I'm asking you to tell me whether it converges or diverges. Now, it is hard. It is hard. If you go, do you have the book?
No.
If you have the book, go to section, I think it is, what section is it? It is 8.9 in our book. If you go to section 8.9, example 7, they show you how to do it. If you're still short, if you still want to learn, look, that's a hard problem. I wouldn't, it takes a while to learn F. But for F, it's really hard to show what its value is. You need to take Calc 3 for that.
Okay.
But you can tell me it converges if you use deductive reasoning. So check out example 7 in section 8.9. And if you, like I said, if you're interested, send me an email and I'll write you up a solution if you still want to know how I would do it.
Okay, that was all for me. Thank you.
Or anybody else? You are welcome. Anybody else going once?
Yeah, I could ask a question with regards to the one on the board, actually.
Yeah, what's up?
Couldn't you define it as y squared minus 4y plus 4, making it a squared? And the way that you do this is by changing the c?
Yeah, you could do that. That's not a problem at all. That's, well, would you even want to use 4 or would you want to use 2?
Let me check. I think it was 4.
Think about, I mean, you can. Look, there's definitely a way of doing that for sure.
I was thinking perfect squares.
Right, but would that work? If you did plus 4, then that wouldn't factor properly.
Maybe I.
For it to factor, you need minus 2. So okay, yeah, okay, fine. Yeah, you can definitely do plus 4. Yeah, you could do it that way. Yep.
Yeah, that's
one way of doing it. There's no doubt about that. But the thing is that that's oftentimes in what we're interested in is we're not interested in y itself. I mean, if we can get it, that's great. But once we have an equation with y's and x's, it's often all we need. Does that make sense?
Yeah.
Yeah. So, but yeah, that's actually a good trick. Did you think of that on your own, or did someone?
Yeah.
That's a good trick, but you can only do that because of that plus c.
Yeah, that's why I used it.
You know where that trick works a lot, and it's not from calculus. That trick works a lot when you're solving these things. So when you take discrete math class and you study these things about modular arithmetic, you have to do, when you solve things that are used for like these divisibility things, which are used for like encryption, you have to do those tricks all the time. You have to creatively add and subtract something so that it factors like that. It's a good trick.
Yeah.
Good stuff. Very good. Good point. Yeah. Anything else?
I could also ask a question with regards to our series.
Okay, yeah.
So we usually do it by integers, like 1, 2, 3 for the n values.
Yes.
But I'm trying to think of a way to do it by like half. So you do n equals 1, n equals 1.5, n equals 2.
Oh, you can absolutely do that.
And I'm thinking of, like, you could also do it by changing the equation and then the bound, because then you divide 2 from like your.
So what you're referring to is one of two things. You're referring to shifting the indices, which is fine. That's something we use all the time. But if you're studying series in general, look, the only types of series that are at least remotely applicable in anything we're going to do would be series where the indices are integers. Right now in calculus, we only study positive integers. But
Yeah, it's just an
when
interesting
you go
question.
into higher level courses, you'll have series that range over all integers. There's a lot of important series that range over the prime numbers, not just integers, but the primes. There's lots of different ways you can define series. You can define them over any set. It doesn't have to be defined over like 1, 2, 3. It could be defined over anything, but we don't touch on that in calculus. In fact, you don't really touch on that unless you take much more abstract math courses where you study series just for the joy, not for the application.
Yeah.
Does that make sense?
My question was more with regards to, can you do this sort of change the bounds by changing the equation itself?
Oh yeah,
Because-
so that's right.
Because what I was thinking of is
In-depth.
dividing 2 from the equation and then increasing the upper bound by.
Right. I mean,
a
I'd have to
multiple
see
of 2.
exactly what you're writing down, but no, you can definitely do that. You can, I mean, I can express the same series using different indices and different expressions.
Yeah.
Right. So that's called shifting the indices. That's absolutely a very common thing. People do that all the time. Yeah.
Yeah. Just wanted to make sure my logic was right.
You can absolutely do that. Yeah. There's some people whose personal preference is they never want to start anywhere other than 1 or 0. So yeah.
Yeah.
And then soon enough, when we start talking about power series, you're going to want to be able to do that so that you can recognize when a particular series is the exponential function or it's something else like sine or cosine. So yeah, that's definitely something you want to do. Someone's asking a question. What is this? Oh, someone in what section? Oh, okay, cool.
You said 8.9 for
Yeah, it's 8.9 in the now section, so it's probably 7.9. Let me check. I have all these books here somewhere. Where's the old book? Actually, I don't have the old book, so I can't tell you what it is in the old book. I believe it's probably 7.9 though.
Okay.
Whatever the improper integral section is, improper integrals. All right. Does anybody else have a question while we're on the question train? Actually, I'm going to stop recording this now. That way, this thing's getting